Hello everyone, welcome to this lecture. In this lecture, we will continue our discussion on on connectivity, cut vertices, cut edges, and we will introduce vertex cut and vertex connectivity, edge cut and edge connectivity, and we will formally prove the relationship between the vertex connectivity and edge connectivity. So let us start with the definition of a vertex cut, which is also called as a separating set. So imagine you are given a graph G, then a proper subset V prime of the set of vertices is called a vertex cut if removing the vertices in V prime disconnect your graph. Okay. So remember, if your graph has an articulation point, then that articulation point itself can constitute a V prime, a potential V prime, whose deletion will disconnect the graph. But it might be possible that your graph may not have an articulation point, in which case you may need to delete more than one vertex in the graph to disconnect it. So the basic idea here is we are now trying to generalize the definition of articulation point in terms of a subset of vertices V prime. So if I take this graph and if I remove the nodes C and node F, then this node G will get disconnected from the network because these edges will also go away. Whereas I can remove the vertices C, B, and A, that will ensure that D and E separate out from the entire graph, right? So here, as of now, there is no criteria on the cardinality of V prime. I'm just checking whether V prime constitutes a vertex cut or not, or whether deleting the vertices in V prime disconnects the graph or not. Okay. So now the question is, can I say that every connected graph which has n nodes has a cut vertex? And the answer is yes, except when the graph is a complete graph, right? So if you take a complete graph of n nodes, right, even if you remove up to n minus 1 nodes, your graph still remains connected, the reduced graph, right? So remember, my V prime should be a proper subset of the vertex set. You can't say that, okay, delete the entire graph itself, because if you delete the entire set of vertices, the entire graph vanishes. So in a complete graph, at max, you can delete up to n minus 1 nodes with a hope to get a disconnected graph, but that's not possible. So now let us next define vertex connectivity of a graph, and the vertex connectivity of a graph is also denoted by this parameter kappa. Okay, kappa of G. So the vertex connectivity of a graph is the size of the smallest vertex cut. Okay, that means the size of the smallest V prime whose deletion will disconnect your graph, or equivalently, it is the minimum number of vertices to be deleted to disconnect your graph. So consider this graph, and for this graph, your kappa is equal to 2. Well, your kappa will be 1 if your graph has an articulation point, but if there is no articulation point, then you may need to delete more than one vertex to disconnect your graph. And in this graph, we don't have any articulation point, so we need to delete at least 2 nodes to disconnect the graph, namely the nodes C and F. Okay. Whereas if I take this graph G, then my kappa here will be 0 because my graph is already disconnected and I don't need to delete any additional node to further disconnect it. Whereas if I take this graph, then the definition that I have given for vertex connectivity does not make sense here, because even if I delete up to n minus 1 nodes here, namely 2 nodes, if I delete say A and B, I will be left with a connected graph, right? So that's why, to take care of the special case of complete graph, I slightly change my definition of vertex connectivity, and my definition of vertex connectivity is the following. It is now the minimum number of vertices which needs to be deleted to either disconnect the graph or produce a graph with a single node. This latter condition is to take care this latter condition is to take care of the complete graph. Okay, so with respect to now this new definition, the kappa or the vertex connectivity for this triangle graph will be 2. So it turns out, and it is easy to verify, that the vertex connectivity of a graph will always be in the range 0 to n minus 1, where n is the number of nodes in your graph. Because if your graph is already disconnected, then you don't need to delete any vertex. Your vertex connectivity will be 0. Whereas if your graph is a complete graph, then you need to delete up to n minus 1 nodes to produce a graph with a single node. Okay. Now my graph will be called as k connected if the vertex connectivity of the graph is at least k. That means the size of the smallest vertex cut is k. Okay. Now we can give similar theory with respect to a collection of edges whose removal will disconnect the graph. So we define what we call as an edge cut. So imagine you are given a graph and a collection of edges E prime will be called an edge cut if deleting the edges in E prime from the graph G disconnects your graph. Okay, so there might be several E primes possible. Right now, when I give the definition of edge cut, I am not focusing on the minimum sized E prime. I will be just given an E prime and I have to check whether deleting the edges in E prime deletes or disconnects my graph or not. So for instance, if I take this graph and if I remove the edge between C and G, C and F and G, then I get a disconnected graph because the node G now gets disconnected from the rest of the network. Similarly, if I remove the node edges between A and D, D and E, and D and C, okay, then okay, I think this should not be, if I remove this edge and if I remove this edge and if I remove the edge, okay, yeah, it constitutes an edge cut because now the node D gets disconnected from the entire network. Okay. So again, similar to the question that we asked for the vertex cut, let us answer this question whether every connected graph which has n nodes has an edge cut or not. Again, the answer is yes, except for the case when your graph is already a graph with just a single node and no edges. Because if you have a graph with a single node and no edges, then you don't have any edge to delete at the first place, right? Otherwise, you always have a set of edges in a connected graph which you can delete to disconnect it. So we now define what we call as the edge connectivity of a graph, and this is denoted by lambda. So what is the edge connectivity of a graph? It is the size of the smallest edge cut, or equivalently the minimum number of edges to be deleted to disconnect the graph. So if I take this graph, then the edge connectivity is 2 because I need to delete 2 edges to disconnect the graph. If your graph has a bridge or a cut edge, then lambda will be 1. But if your graph does not have a bridge, then you need to delete more than 1 edges to delete the graph, disconnect the graph. If you take this disconnected graph, then the edge connectivity will be 0 because it is already disconnected and I don't need to delete any edge to disconnect it. But now if I take this graph which has no edges and just a single node, then this definition does not make sense here because I can't delete any edge in this graph to get a disconnected graph. So to take care of this special case, I modify my definition, and my modified definition of edge connectivity is the following. I define edge connectivity to be the minimum number of edges which needs to be deleted to either disconnect the graph or produce a graph with a single node. This latter condition is added for taking care of this special case. because if I apply this definition to the special case, then I get lambda equal to 0 because my graph is already a graph with a single node and I need to delete 0 number of edges to produce a graph with a single node. Okay. So again, it is easy to verify that your edge connectivity will be in the range 0 to n minus 1. 0 for the case when your graph is already disconnected, and or for this particular case when your graph is just consisting of a single node, and n minus 1 for the case when your graph is a complete graph. If your graph is a complete graph, then you just delete n minus 1 edges incident with any node, then that node gets disconnected from the rest of the network. Okay. So now we want to fit some upper bounds on the vertex connectivity and edge connectivity. So let's first prove an upper bound on the vertex connectivity. So my claim here is that for any connected non-complete graph, I stress connected non-complete graph, the vertex connectivity is always less than equal to the minimum degree that is possible in your graph. That means you take the vertex V, which has the least degree in the graph, say the degree is D, then my claim is that kappa of your graph G is always less than equal to D. Okay. So a simple proof for this fact is the following. So consider this graph or consider any arbitrary connected non-complete graph and focus on the vertex V which has the least degree. Namely, the degree of the vertex V is D. That means the node V has D number of neighbors. Okay. Now what happens in this graph if all the neighbors of the vertex V are deleted? So for instance, in this graph, the vertex C has the the vertex G has the least degree. Okay. In fact, vertex E also has the same degree as vertex G. So what I am saying is, if you remove all the neighbors of the vertex which has the least degree, then that vertex V gets disconnected from the rest of the graph. So that shows that you don't need to delete more than D number of nodes in the graph to produce a disconnected graph. The maximum number of nodes that you need to delete is D. But then now you might be wondering that as per the argument that I have given, why it is less than equal to? Why not exactly equal to? You might argue that I definitely need to delete exactly D number of nodes to disconnect the graph or to disconnect the node V from the rest of the graph. Well, that's not necessarily true. If you consider this graph, then here the minimum degree is equal to 2 because you have a node G which has degree 2, you have a node F which has degree 2, you have node D which has degree 2, you have node E which has degree 2 and so on. So you might argue that definitely I need to delete at least 2 nodes to disconnect a graph. Of course, if you can delete all the neighbors of D or all the neighbors of E or all the neighbors of F or all the neighbors of G, you get a disconnected graph. But you don't need to do that much labor. Why? Because if you just delete the node C, your graph gets disconnected. So the vertex connectivity kappa here is 1, which is strictly less than the minimum degree in the graph. Okay. Now let's derive some upper bound on the edge connectivity. And again, I take the case of a connected non-complete graph, and the upper bound here remains the same. My claim is that the edge connectivity of a graph is always upper bounded by the minimum degree that is possible in your graph. Okay. So the proof is again very simple. Let V be the vertex with least degree. Of course, you can have multiple vertices with the same least degree. So focus on one of the vertices V. And then argue that what happens if all the edges incident with the vertex V are deleted. So for instance, in this graph, G is the vertex V which has the least degree. So what I am arguing here is that if you delete all the edges which are incident with this vertex G, the vertex G get disconnected from the rest of the graph. So that shows you don't need to delete more than least degree number of edges in your graph to produce a disconnected graph. But then again you get the same question that as per this argument, one may get the feeling that lambda should be exactly equal to the minimum degree in the graph. Why less than equal to? Well, again consider this graph. Here the minimum degree is 2. So the vertex F has degree 2, the vertex G also has degree 2. So that means that if you remove these two edges, the node F gets disconnected, and in the same way, uh, if you remove these two edges, the node G gets disconnected, and so on. So you might say that I definitely need to delete two edges to produce a disconnected graph from this connected graph. Well, the answer is no, because if you remove this edge, which is a bridge in this overall graph, your graph gets disconnected. So the lambda here is 1, not 2. Okay, so now we want to establish a relationship between the vertex connectivity and edge connectivity. And there is this very nice theorem statement which says that you take any connected non-complete graph, then the vertex connectivity is always less than equal to the edge connectivity. Okay, so let us prove this. The proof is uh, very simple. So imagine you are given a connected non-complete graph. Why I'm taking non-complete? Because for a complete graph, this inequality is always true. Both kappa as well as lambda are n minus 1. Okay, so that's why I'm taking the case of a non-complete graph and connected graph. Because again, if I take a disconnected graph, both kappa and lambda are 0 and the inequality holds. So I take a connected non-complete graph G, okay, which is an arbitrary graph, and imagine that E prime constitutes an edge cut for G, the minimum edge cut for G, which has lambda number of edges. Okay, that means if I remove the edges E1, E2, E lambda from the graph, my graph gets disconnected. Okay, and say the endpoints of the ith edge EI is UI, VI. So these are the endpoints of the edge EI. So you can imagine that if I remove the edges E1, E2, E lambda from my graph G, I get two connected components, component C1 and component C2. So you can imagine that the structure of your graph is something as follows. You have the vertices and edges structured in such a way that you can interpret E1, E2, E lambda as kind of bridges between component C1 and C2, so that the one of the endpoints E1 is in component C1 and another endpoint, namely V1, is in C2, and so on. Okay. By the way, here it's not necessary that all the nodes U1 to U lambda or V1 to V lambda are distinct. It might be possible that you have just U1 in component C1 and all the edges E1, E2, E3 up to E lambda has U1 as one of its endpoints. Okay, that's also possible. But similarly, you might have a case where the edges are such that you only have V1 as the only node in C2 and all these edges E1, E2, E3 up to E lambda as V1 as one of its endpoints. So that's why it's not necessary that U1 to U lambda and V1 to V lambda are all distinct. But for pictorial simplicity and for pictorial understanding, I am representing them as lambda number of U vertices and lambda number of V vertices. Okay, and as per my property, as per my definition, E prime or this collection of edges E1 to E lambda constitutes an edge cut. That means even if you don't delete a single edge from this collection of edges, the graph G still remains connected. Only when you delete all these lambda edges, the graph gets disconnected into components C1 and C2. That's the property of this collection of edges E prime. Now from these edges, I have to show the existence of at least I have to show the existence of some lambda number of vertices whose deletion will definitely disconnect my graph. Because if I can show you the existence of some lambda number of vertices whose deletion will disconnect my graph, then that shows that my vertex connectivity is also upper bounded by lambda, and hence it shows that the vertex connectivity is upper bounded by edge connectivity. So let us do that. So first delete the lambda minus 1 u vertices, namely you delete the endpoint of E1 from the component C1. You take the edge E2 and delete the edge U2 from the component C1, and similarly you take the delta minus 1th edge and delete the U vertex from the component C1. Okay, so you have deleted lambda minus 1 vertices from your graph G, and remember, as per the definition of deletion of a vertex, when I delete a vertex, all the edges incident with that vertex also gets deleted from the graph. So my new graph, I call it as the graph H, and my new graph H will look something as follows. Okay, the edge E lambda is still there in my graph G. Okay, and because of that, the endpoint U lambda is still there in my graph G. Okay, now what can I say about my graph H? My graph H is still connected graph. It's not yet disconnected because I still have one bridge or one edge going from U lambda to the component C2, and that will ensure that everything in C1 is reachable to C2 via the edge E lambda. Okay. Now here is the crucial claim. My claim is that the edge E lambda constitutes a cut edge or a bridge for the reduced graph H. Okay, and the proof is very straightforward. If this edge E lambda does not constitute a cut edge for the reduced graph H, that means that even if I delete this edge E lambda, still somehow everything in C1 is reachable to C2. Okay, that's the implication. But if that is the case, then I get a contradiction that this collection of edges E prime, which I assume to be the minimum number of edges whose deletion will disconnect the graph G, is not a valid assumption, right? So I remember I assume that as soon as I remove the edges E1 to E lambda, my graph gets splitted into two parts, C1 and C2, so that such that nothing in C1 is reachable to C2 and vice versa. So I have already removed E1 to E lambda minus 1, and now I am arguing that if I remove E lambda, my graph H gets splitted into C1 and C2, such that C1 is completely disconnected from C2 and vice versa. If that is not the case, that means I need to further delete more edges even after removing E1 to E lambda to disconnect my original graph G, which goes against the assumption that E prime was the collection of minimum collection of edges whose deletion will disconnect my graph, right? So I get this implication. Remember, I have already removed lambda minus 1 vertices. And now I have to show that if I add one more vertex to this collection of lambda minus 1 vertices, which I have already deleted from G, I get a vertex cut for my graph G. Now you might be tempting to say that if I include U lambda to this collection of vertices U1 to U lambda minus 1, it will always constitute a vertex cut for G. Or you might be tempting to say that if I include V lambda to the collection of vertices in u1 to u lambda minus 1 that will constitute a vertex cut for G. Well, you can't necessarily do that. You have to argue here based on cases. So since I have argued that the edge E lambda constitutes a bridge or a cut edge for the graph H, I can definitely say that one of its endpoint is a cut vertex for the reduced graph, because then only the edge E lambda can constitute a bridge. And this is a property which is there with respect to any bridge or any cut edge of a graph. I can always say that if I have a cut edge in a graph, one of its endpoints is definitely a cut vertex. Because if none of the endpoints of the edge is a cut vertex, then at the first place that edge was not a cut edge. A very simple fact. Now I have two possible cases. If u lambda is a cut vertex for edge, then I can say that the collection of u1 to u lambda minus 1 and the vertex u lambda constitutes the vertex cut for G, right? Whereas case 2 is the following. If v lambda is a cut vertex for the graph H, then I can say that the collection of u1 to u lambda minus 1 along with v lambda will constitute a vertex cut for G. So you can't always say that it's u1 to u lambda which is always a cut vertex for the graph G. It depends. Once you have removed the first lambda minus 1 edges and one of the endpoints of those lambda minus 1 edges in one of the components, you will be left with a cut edge, and your graph may be something as follows. So your graph may be something like this, right? So you might have got u lambda, and then you have v lambda, and then the rest of the graph is still there. That means your reduced graph H is something like this. In that case, you can't say that if I just delete u lambda along with u lambda minus u1 to u lambda minus 1, I get a disconnected graph. No, by removing u lambda, you get the whole graph C2 as your reduced graph, which is connected. So in that case, you have not obtained a cut vertex, right? It's only when you remove v lambda that this portion of C2 gets disconnected from u lambda, right? So it depends upon which endpoint of the cut edge. E lambda is a cut vertex for the reduced graph, and that cut vertex along with the lambda minus 1 vertices which you have already removed will give you a vertex cut for the original graph G. Okay, so that's a subtle point, the two cases. Otherwise, the rest of the proof is straightforward. So now let us unify the relationship between the vertex connectivity and edge connectivity, taking care of various cases. We just proved that for any connected non-complete graph, the vertex connectivity is always less than equal to the edge connectivity. We know that for disconnected graphs, the vertex connectivity and edge connectivity are same, namely 0. And for complete graphs, we know that the vertex connectivity and edge connectivity are same and exactly equal to n minus 1. And we also proved that for connected non-complete graphs, individually the vertex connectivity is upper bounded by the minimum degree, and the edge connectivity is also upper bounded by minimum degree. So unifying all these things, we can say the following. Irrespective of whether my graph is connected, disconnected, complete, non-complete, the vertex connectivity is always less than equal to edge connectivity, and edge connectivity is always less than equal to the minimum degree in the graph. This relationship takes care of all the cases here: complete, non-complete, connected, disconnected, and so on. Okay. So that brings me to the end of this lecture. Just to summarize, in this lecture we discussed about the vertex connectivity, edge connectivity, and we proved the general relationship that exists between vertex connectivity and edge connectivity. Thank you.